Welcome to this comprehensive guide on model evaluation and practical implementation in machine learning. Understanding how to rigorously assess your models is paramount to building reliable and effective systems. Without proper evaluation, even the most sophisticated algorithms can lead to misleading conclusions and poor real-world performance. Our journey begins with structuring data effectively, a foundational step that ensures unbiased model assessment. We will then delve into various metrics for both categorical and continuous outcomes, providing you with the tools to interpret your model's strengths and weaknesses. Finally, we will tackle the critical challenge of class imbalance, a common issue in real-world datasets that demands careful handling. When developing a machine learning model, our primary goal is to create a system that generalizes well to unseen data. A model that performs perfectly on the data it was trained on but fails on new data is essentially useless. This phenomenon is known as overfitting. To prevent overfitting and accurately estimate a model's generalization capability, we must evaluate it on data it has not encountered during training. This necessitates a strategic approach to data partitioning, ensuring that our evaluation is fair and representative. Effective data splitting is the cornerstone of reliable model evaluation. It allows us to simulate how our model will perform on new, unseen data. Two primary techniques are widely used: holdout validation and k-fold cross-validation. Holdout validation is the simplest and most common data splitting technique. The dataset is divided into two distinct subsets, a training set and a test set. Typically, 70% to 80% of the data is allocated for training, and the remaining 20% to 30% is reserved for testing. The model learns patterns and relationships exclusively from the training set. Once training is complete, its performance is then assessed solely on the test set. This provides an unbiased estimate of how the model will perform on new data. While straightforward, holdout validation has some limitations. The performance estimate can be highly dependent on the specific split of the data. If the test set happens to be unrepresentative, the evaluation might be skewed. Furthermore, a significant portion of the data is withheld from training, potentially leading to a less robust model, especially with smaller datasets. K-fold cross-validation addresses some of the shortcomings of holdout validation by making more efficient use of the available data. In this technique, the entire dataset is first divided into k equally sized folds or subsets. A common choice for k is 5 or 10. The process then iterates k times. In each iteration, one fold is designated as the test set, and the remaining k1 folds are combined to form the training set. The model is trained on this combined training set and evaluated on the single test fold. This procedure is repeated k times, ensuring that each fold serves as the test set exactly once. The final performance metric is then calculated as the average of the k individual evaluation scores. This approach provides a more robust and less biased estimate of the model's performance, as every data point gets to be in a test set exactly once. K-fold cross-validation offers a more stable and reliable performance estimate compared to a single holdout split. It reduces the variance of the performance estimate and utilizes the entire dataset for both training and testing over the course of the process. However, it is computationally more expensive, as the model must be trained and evaluated k times. When dealing with classification problems, where the model predicts discrete categories, a specific set of metrics is essential for evaluation. These metrics provide a nuanced understanding beyond simple accuracy. The confusion matrix is a fundamental tool for understanding the performance of a classification model. It is a table that summarizes the number of correct and incorrect predictions made by a classifier, broken down by each class. It consists of 4 key values: true positives, true negatives, false positives, and false negatives. True positives are instances correctly predicted as the positive class. True negatives are instances correctly predicted as the negative class. False positives are instances incorrectly predicted as the positive class when they are actually negative. False negatives are instances incorrectly predicted as the negative class when they are actually positive. Accuracy measures the proportion of total predictions that were correct. It is calculated as the sum of true positives and true negatives divided by the total number of instances. While intuitive, accuracy can be misleading, especially in cases of class imbalance. Precision quantifies the proportion of positive identifications that were actually correct. It answers the question, of all instances predicted as positive, how many were truly positive? Precision is crucial when the cost of a false positive is high. Recall, also known as sensitivity, measures the proportion of actual positives that were correctly identified. It answers the question, of all actual positive instances, how many did the model correctly identify? Recall is important when the cost of a false negative is high. The F1 score is the harmonic mean of precision and recall. It provides a single metric that balances both precision and recall, making it particularly useful when you need to consider both false positives and false negatives. A high F1 score indicates good performance on both fronts. The receiver operating characteristic (ROC) curve plots the true positive rate against the false positive rate at various threshold settings. The area under the curve, AUC, of the ROC curve provides a single scalar value that summarizes the model's ability to distinguish between classes across all possible thresholds. A higher AUC indicates better overall discriminative power. For regression problems, where the model predicts a continuous numerical value, different metrics are required to assess performance. These metrics quantify the difference between the predicted values and the actual values. Mean absolute error, MAE, measures the average magnitude of the errors in a set of predictions, without considering their direction. It is the average of the absolute differences between predicted and actual values. MAE is robust to outliers, as it does not square the errors. Mean squared error, MSE, calculates the average of the squares of the errors. By squaring the errors, MSE penalizes larger errors more heavily than smaller ones. This makes it sensitive to outliers, which can significantly inflate the MSE value. Root mean squared error, RMSE, is the square root of the MSE. It brings the error metric back to the same units as the target variable, making it more interpretable than MSE. Like MSE, RMSE is also sensitive to outliers. R squared, R superscript 2, also known as the coefficient of determination, represents the proportion of the variance in the dependent variable that is predictable from the independent variables. It indicates how well the model's predictions approximate the real data points. An R squared of 1 indicates that the model perfectly predicts the target variable, while 0 indicates no linear relationship. Class imbalance occurs when the number of observations belonging to one class is significantly lower than those belonging to other classes. This is a common problem in many real-world datasets, such as fraud detection, rare disease diagnosis, or anomaly detection. When a dataset is imbalanced, standard machine learning algorithms tend to be biased towards the majority class. They might achieve high overall accuracy by simply predicting the majority class for most instances. However, this often comes at the cost of poor performance on the minority class, which is typically the class of greater interest. For example, in fraud detection, if only 1% of transactions are fraudulent, a model that always predicts not fraud would achieve 99% accuracy. This high accuracy is misleading because the model completely fails to identify any fraudulent transactions. Therefore, relying solely on accuracy in imbalanced scenarios is highly problematic. Several strategies can be employed to address class imbalance and improve model performance on the minority class. These can be broadly categorized into data-level approaches and algorithm-level approaches. Resampling techniques modify the distribution of the dataset. Oversampling involves increasing the number of instances in the minority class. Techniques like SMOTE, or synthetic minority oversampling technique, create synthetic samples that are similar to existing minority class instances. Undersampling involves reducing the number of instances in the majority class. This can be done randomly or by more sophisticated methods that remove redundant or noisy majority class samples. Algorithm-level approaches involve modifying the learning algorithm itself or its parameters. Cost-sensitive learning assigns different misclassification costs to different classes, penalizing errors on the minority class more heavily. Another approach is to adjust decision thresholds after training. For instance, in a binary classifier, instead of using a default 0.5 probability threshold, we might lower it to increase recall for the minority class. When evaluating models on imbalanced datasets, it is crucial to use appropriate metrics. As discussed earlier, metrics like precision, recall, F1 score, and AUCOC are far more informative than accuracy. They provide a clearer picture of the model's ability to correctly identify instances of the minority class, which is often the primary objective in such scenarios. Implementing model evaluation effectively requires more than just knowing the metrics. It involves an iterative process of model development, evaluation, and refinement. Always consider the specific problem you are trying to solve and the real-world implications of different types of errors. Choosing the right evaluation metric is paramount. A high recall might be critical in medical diagnosis, while high precision might be essential in spam detection. Domain knowledge plays a crucial role in making these informed decisions. Remember that no single metric tells the whole story. A holistic view using multiple metrics is often best. Model evaluation is not merely a final step but an integral part of the machine learning workflow. By understanding and applying robust data splitting techniques like holdout and k-fold cross-validation, you ensure that your model assessments are reliable. Mastering performance metrics for both categorical and continuous outcomes allows you to deeply understand your model's behavior. Furthermore, effectively managing class imbalance is a vital skill for building practical and impactful machine learning solutions in the real world. These principles empower you to develop models that are not only accurate but also truly useful and trustworthy.